Now, we had our Arduino connecting to this AC-DC adapter here. But we could have just connected it right off this rectifier with a voltage divider and sent it through. A voltage divider is made usually for reading a current. Reading a voltage. Or used for, having a rectified output. So reading a voltage, basically. Here's another voltage divider for voltage reading, etc. Also for reading the voltage of a battery, we got voltage dividers here. But, actually they're not voltage dividers. It doesn't have to divide it because the battery's voltage is low enough for the digital pins of Arduino to read it safely, or the analog pins. So anyways, I realize I don't think we need this AC-DC adapter. We can use voltage dividers to provide for our power needs for the microcontroller. I honestly believe this is doable, guys. Well, let me check that donation. Oh, $3.55, thanks, man. Alright, so what I'm getting at is using an AC-DC adapter isn't necessary because the power we're going to draw from that adapter is so low. Now, Arduino only pulls 45 milliamps. Now if you multiply that by 10, that's 450 milliamps. If you multiply that by 2, that's 1 amp. So 10 and 2 is 20, so times 20 is an amp. So it's a 20th of an amp. And 5 volts running 1/20th of an amp is what amount of watts? Well, 5 volts divided by 5 is 1 watt. So if it was 1/5 of a watt, 1/5 of an amp times 5 volts, that would be 1 watt. But we're under that because we're divided by 20. So divided by 5 is 1, and then another divided by 4, that's 0.25 watts. Now, a typical resistor that comes in a resistor assortment pack on eBay is half a watt, capable of handling half a watt. And we only want 1/4 of a watt. So a typical cheap resistor on eBay can handle the amount of current needed by an Arduino. I established that just with mental math. So we don't need a whole AC-DC adapter here, which was a big chunk of the total size involved in my project. It was taking up a lot of room. It's a big box. If we take that box out and replace it with 2 little resistors, because the box has inside it capacitors, and it has a diode bridge rectifier, and it has an actual transformer in it. So it's, a decent sized box, AC/DC adapter box. We get to get rid of that and just use 2 little resistors to power our Arduino off of this rectifier. So getting rid of this box will reduce the size of my project tremendously. Huge. Which will make my power supply design even smaller and way better. So I'm doing it. I don't care, guys, I'm doing it. Yeah. This is for sure a must-do. So, let's make it happen real quick. And I'll add it to my to-do list as well. We just need to bring all of this and bring this over like so. Okay. We have to recut our whole thing to bring it to the left more. Okay. What are we doing? Oh, we're in the electronic session here. Okay. So, and I'll bring these guys over as well. Well, I have to. Maybe put the voltage divider in here. And down. Alright, so we do that. Yeah, let's do that. This is so funny. I can't believe I'm making a major change again. But hey man, that's why it's kind of good that my first project is just a slow process. Okay, so I'm getting rid of this. The lower is gone. I never liked it to begin with. I didn't like having to use something so off the shelf, you know, because I'm trying to do everything like low level, so nice everything. I just want to have a bunch of modules to put in. I want to like do electronics project, you know. At least my first major electronics project, I wanted to be like really low level. Okay. Now we zoom out. And this will be the trick. Let me paste in one of these voltage dividers. So we'll add this one to the one. Okay. And we'll get these. Let me get this. Like so. I think we're good to go. So I never thought a voltage divider could do anything other than basically take current readings. But somebody gave me the idea in a YouTube comment, hey, why don't you use a voltage divider to power your device? And I explained to them, well, a voltage divider can only handle very low amount of current because whatever voltage is lost in the divider is wasted through heat. And I don't know, it's just using voltage dividers to power devices like a motor can't be done because too much current needs to flow through it, and resistors would just get really hot. But to power a microcontroller, resistors can handle that amount of heat and that amount of current. They can handle up to half a watt of power going through them for a standard resistor. You can get big resistors that can handle more. So it's totally doable. It's totally worth it. So I'm excited, man. So let's see. Well, we can get rid of this. Boom and boom. We're going to need two of these voltage dividers. One will go, okay, we'll have this one come around down here, and we'll have the second one come straight to here. So let me just go ahead and copy it real quick. Boom. Control C, Control V. One of the voltage dividers will power the Arduino, and the other one will take care of powering the MOSFETs, which has to be 10 amp or 10 volts because they're 10 volt MOSFETs. This is a radical change, guys. I'm very excited about it. I'm a wild animal for doing this. So late game, man. We're gonna make a huge change like this. The changes just keep flowing. It's amazing. I keep getting ideas for this circuit line. Okay. And now we do this. Okay. Okay. Let me just get this bad boy. Oh shit. Okay, let me bring all these notes down first. Like so. Okay, bring the lines down like so. And you down like this. Oh. And now I can bring this line down. I erase this one location. Okay, all the way back. Follow it. Okay. And this guy. Watch out there. Don't erase this. Good. You need to connect again. Like so. Keep erasing back now. Alright, now we want this line to come down under. So we're just going to bring it down. That's the whole point of everything else down. We want this one all the way over to our voltage divider, which will provide our 10 volts to our MOSFETs. And then we want this guy to also come to it. Okay, we'll get rid of this. Like so. We still have to update the value of these resistors. I just have what I had originally. More copy them. We're just only wiring. Okay, and then this line gets erased. So, he's on. And he's also on. And this uppermost one is on. This is going to move down. Okay. Go this way, over here. And using a voltage divider, Arduino, off of a rectified AC. That is just crazy. Just take AC, stick it in the rectifier, and then all you have to do is voltage divide off that. So whatever voltage you want in DC, and it's going to send a low current to some device at the appropriate voltage. Using just diodes and resistors now have voltage and current at a desired amount. Well, we have perfectly correct voltage and get all the smoothing and capacitance down through this little circuit, which has a regulator, electric capacitors, capacitors. I'll smooth everything out, get all perfectly, even more detailed capacitors, so that Arduino is going to be getting voltage to this line. So yeah, man. So this one will provide the 10 volts coming out to our low side switch to this high side switch, which requires 10 volts. It is a IRA40 voltage across 8 source 10 volts on, 20 volts max across 8. So that will be coming from here. And then this one will give, I want to go after 9 volts, because I believe the 75 regulator, yeah, needs to 30 volts. I'm going to stick at 9 volts coming down, and then it'll take over from there with 75 regulator. There's no disaster here. Okay. It's so nice to put the lower away. I didn't need it after all. It's going to make so much smaller, power. We truly transform this now. That's no transformer involved at all. That's what I'm talking about. Transformers are big, heavy steel things. I want to know. We're going for lightweight, high power, unlimited power, super lightweight, and small. That is the best thing you can do for robotics. Small, lightweight, unlimited power. Boom. I'll take it. So we have it. This is beautiful. Oh yeah. Oh yeah. And I'm going to do the value, so. Okay. We need a calculator to figure out these values. This thing, the starting voltage coming off of here is 155 volts DC, as it says here. So, we could say that it will range between. Well, wait a minute. If the fuse blows, my microcontroller will be on. Is that a problem? I think that is a problem. Maybe we should put the fuse even before the rectification. Yeah, I'll just get the fuse. Let's move it. Okay. Uh-oh. Alright, we need to move everything over again. As far as these guys go. Like that. Okay. And so I can come in. You can come across. So. Okay. Let me just go on this then. Alright. So, this will range from, let's say, like 120 volts to 165 volts. Okay. I just made it up, but that's like extreme circumstances. 120 volts. Okay. 165. Alright. What the heck? Okay, 120 times 5 equals, divided by 155 equals 3.87 volts, which would be way too low. So, let's try 120 times 5 divided by 50 plus 5. That's 10.9 volts. We want 10 volts, that's perfect. So, let's just change it to 50. See how that works out for everyone else. This is tentative so far. I think it'll work. Okay, let's try 120 times 5 divided by 55 is 10.9 volts, which is great. Okay, and then 165 times 5 divided by 55 is 15 volts, which is also great. It's going between 10 to 20 volts as the gate voltage for these bigger MOSFETs, these non-logical MOSFETs, and channel power MOSFETs. Okay, so this will be just at 15 volts. Okay. Between 10 to 20 volts is safe. Okay, so we have to make this 50 for a resistor, supposing the current's going to look okay. Alright, the current to draw it will allow 120 volts divided by 1 milliamps. 3 zeros. 3, 6, 3, 2.1 milliamps. Okay, 2.18 milliamps. And he's safe. No, that's not very true. Yeah, it is. Okay, that's pretty much 60 for this. And here we're doing 165 volts divided by 55,000 equals 103, which is the same as 3 milliamps. Okay. Okay. And then this one. We want this one to go out pretty close to actually. Heck, we do the same. Wait, what? 10 to 15 volts is fine. Oh know what? We can use that for both. Dang. That's crazy. I didn't see that coming. Alright, one voltage drive, so what about? Oh, okay, hold on. We need mercies. Boom, 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 boom. Okay. I'll take this, move it to right here. Okay. And turn that, okay. I flew. No, it's not the current system for my 6-1 custom power supply design from ground up and then across the building. I came up with some really cool tricks that would reduce the total size of all the parts. You need a super good trick. Basically, powering Arduino voltage divider instead of using AC to battery power, which is crazy sounding. It doesn't work. Okay. Boom. And beautiful. Okay. Start with that. Start with that. Okay. Okay. And now do this. Wait. Come here, like that. Boom, 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 boom. Okay. So funny how much I keep coming back to this schematic. This thing has been edited and edited and edited, but each time I'm editing, I'm probably learning a lot. And memorizing this whole page. So the more time I spend on this page, the more I can visualize it. And it pretty much has every single principle of electronics demonstrated. It has every type of thing. Inductors, voltage regulators, switching, voltage converters. It has amperage regulation, voltage readers, microcontrollers, MOSFETs. It's like every single fundamental of electronics is in there. Motors, motor surge protection circuits, backflow protection. It's got batteries, battery management software, battery charging circuits. It's got buttons, you name it. Rectifiers, fuses, AC and DC is dealt with. Homemade microcontrollers, or microcontroller support circuitry. It's got notes on everything. It even uses Arduino Nano here. Huh, you're wrong. The programming that I'm having intentions to build would cost billions of dollars. Billions. That I'm going to be building throughout my lifetime. It's going to take decades. It will be the most advanced artificial intelligence in the history of mankind. You can't just hire any old kid to program the most advanced artificial intelligence in the history of mankind. It's not possible. There are very few people who could even understand that. And I'm one of the few. Okay. Alright, I finished what I set out to do today with that. Cool. Alright, so let me go ahead and minimize that and then add the couple of changes to my notes for my electronics to-do list. Alright, 2500 plus 300 equals 2800. Okay. I realized the amps here don't have to be enough amps to run an Arduino because they need to be enough watts to run an Arduino. So at 17 volts, having the amps the Arduino needs, which is 45 milliamps, is not what we need, because we need 45 milliamps at 5 volts. So a quarter of a watt. 17 times 118 milliamps is too high because these resistors can only handle a quarter of a watt. 17.68 times 0.118 amps equals 2 watts. That's too much. We can't allow 2 watts through. It has to be a quarter of a watt through, so you need to divide that wattage by 4. About 0.52. I think 2500 and 500 was a good amount. Let's see, 2500, wait, 165 times 500 equals, divided by 3000 is 27.5. 300, okay, 2500 and 300. We'll do 165 times 300 equals, divided by 2800 equals 17.67. Okay, yeah, so 300 and 2500. And then we'll do 2500 plus 300. 165 divided by 25 or 2800. 0.058 or 58 milliamps. Okay. 0.058 times 17.68 equals, that's 1 watt. Divide that by 2. So times 2, 2500 and 300, 5K and 600 then. I think that's it. 5K and 600. Okay, so let's run the math on that. 165 times 600 divided by 5600 is 17.67 volts. 17.68 volts, same. Okay, and then 165 divided by 5600, 0.029 amps, or 29 milliamps, okay? 0.029 times 17.68 gives me 0.52 watts, which is around half a watt. These resistors can only handle a quarter of a watt, but this is at 165 volts. It's going to generally be 155 volts. So let's try the math at 155, the nominal. 155 times 600 divided by 5600. That's 16.6 volts. Okay, and then we got 155 divided by 5600, 0.027 amps. 0.027 times 16.6 equals 0.44, which is around half a watt still. I'm kind of okay with that. Because the Arduino will draw what it's going to draw, right? Well, then again, if the Arduino is going to draw what it's going to draw and it never draws too high or too long too high, I guess even leaving it at the values we had would be fine. It's just the values we had would allow too much to be drawn, in theory, if we put too much load on it. But we're not planning to put too much load on it. Well, I still feel more comfortable with 5K and 600, so we'll just do that. I gotta update all the values then. So, but yeah, it might not matter. As long as there's enough that can get through, we just have to make sure we don't send too much through to burn out the resistors. That's all. 5,600 or 5,000 plus 600. .021. .029. And then this is misleading. .45 milliamps at 5 volts, not 45 milliamps at any voltage. So it needs a quarter watt. So you multiply the voltage you're giving it by the amps you're giving it to get the total watts you're giving it. And as long as you're high enough in watts. watts, just not too few. The extra watts will not actually be used as long as our load does not try to pull that many. The resistors are only rated for 1/4 watts. So we are hoping the Arduino and MOSFETs do not pull more than that, which they should not, according to the data sheet for the T-Mega 328P, which says it only pulls 45 milliamps at 5 volts or 0.225 watts. Okay, let's take this, 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 and this, and move them up. Whoa. We might have another problem, guys. Oh, great. Oh. Ugh. I just realized that I think my circuit would start on fire. Because 5k ohms plus 600 ohms is 5600 ohms. And 155 volts divided by 5600 will give you the current, which is 0.027. 0.027 times 155 is 4.3 watts. These are only rated for 1/4 of a watt. This is 4.3 watts. everything was fine as far as what I'll be drawing from it off of these two lines. But it's this line that I'm worried about. The actual passage from the main line through these two resistors and up to here. That's going to be a problem, I think. Alright, if it's 4 watts, we need to divide that by 4. 0.025. No. Divided by 8. Oh. Divided by 10? Wait. Oh. Oh my gosh. Let me see something. Cool. Guys, I can probably get some big fat resistors off this board here. Some of them are big. And that might be my ticket. Let's see. We bought some big resistors one time. I think there were... I don't remember. I'm gonna keep checking these. That was 450 ohms. We want a 600 ohm and a 5k ohm. 5k ohm resistor. $4K7, 5 watt. What? Guys, I found it! Heck to the no. These, right here, look at this. Right here. Can you read that? It says 4K7. Let's see if you can see. 4K7, 5%, 5 watts. Some big white resistors. Okay, if you have that, plus this one is a 500 ohm. Well, it's 456 ohm. This is close to what I needed. 5K and 500 ohm. And they're big. This is a big one. So this, I don't know what amount of watts this is, but I imagine it'd have to be like 3 watts or something. Because it's big, that means it's designed to take a lot of heat. Notice how they kept it far away from the board because they know it's going to get hot. This is designed to have a lot of heat go through it. So I think this one and that one will do the trick for me. I really do. So let's get those bad boys out. This is a board from an old TV, and it's saving us from having to buy parts. Resistors of this size, from what I was seeing, are like $1 each or 80 cents each, and you can buy them in like a 10-pack. So this is saving me a couple bucks. That's pretty neat. It's unlike the 1/4 watt resistors, the real tiny ones, the standard size. These are a little more expensive, and you can't just buy them in a multi-pack for like 3 cents each. Like, these are beefy ones, and you got to pay some money. They're not as high in demand, because people don't need giant resistors that often. But since I'm using resistors as a power supply for a microcontroller, I actually do need to have kind of big big beefy resistors, because the beefy ones can handle the amount of watts that are going to be flowing through, which is going to be high. Sort of high. I mean, not that high, but kind of high. It's going to be like 4 or 5 watts flowing through it. Got one side. Okay, so here we got one resistor out. I just grabbed it on the back side and heated this side, and then try to get this bad boy out if we can. Whoa! It has 4 legs? Wow. This is so cool. Alright. This is gonna be tricky. You know what? I might actually have to use my thingamabob for the first time ever since I bought it. Let's see. It's a solder sucker thing. So the idea is to heat it up and then suck the solder out. I'm not sure. We might actually have to use this thing. Kind of worried about it. I don't like... I don't know, man. Okay. So first... Oh, I know what I need. I need to tin this bad boy. Poor guy. Alright. Where did I set that solder sucker down at? Here it is. I feel like I should watch a video on how to solder suck to refresh my memory, but... Oops. Huh? Did I just do it? I think I just did it. Whoa! What happens to the solder though? Where's it going? This is magical. But yeah, this is the circuit board from an old TV, yeah. Cool, it's working. I think. Probably not working good enough, though. Okay, let's try to wrestle it out now. We got... Ooh! Ooh! We did it! Okay. So there we have it. 5 watt, 4K7. And we're golden. Another example of why hoarding is good. We just saved ourselves a couple dollars and having to wait a month to get a part. I'm loving it. That was really encouraging. Alright, so let's try to put in... Where did the other resistor go, though? I had 2. I took out the first one. I set it down somewhere. Oh, no. Oh, here it is. Okay. I want to measure them both just to make sure they're correct. So... .75 k ohms. And 0.46 k ohms, which is the same as 460 ohms. Okay. Now I want to test those measurements in my circuit. It was very close to the values we already calculated out. We'll probably be okay. Can't believe they threw it in the trash. I know! They could have built a robot with it. What an idiot. Turning TVs into robots. That's the way to go. Okay, so, 4,700 plus 460. Let's see. Was it 460? Yeah, wasn't it? Let me double check. I forgot already. I should have wrote it down. $460 and $4.75K. 4750. Okay. Alright. Now. 120 divided by 5210. And then this one is, again, 5210. 165 divided by 5210 equals 0.032. Divided by 5210, 0.023. And then this part is going to be 460 and 460, 460, 460. And this part is going to be 4750, 4750. Okay. 120 times 460 divided by 4750 plus 460. 10.59. Perfect. And then 165 times 460 divided by 4750 plus 460. 14.57. Okay, and then 14.57 times 0.32. 0.032 is around half a watt. It will provide to the microcontroller, so that's fine. Now, we are concerned about the total watts that pass through from here through these two resistors and into here. That's like a short circuiting, so the load has to be enough, or we can calculate the watts passing through that. So it's 155 volts divided by 4.75 K, so that's 4750 plus 460. That's 0.02 or 0.03 amps times 155, 4.61 watts. Because amps times volts equals watts. 4.61 watts will be going through this. They're rated for 5 watts. Well, one of them is. The other one, I don't know. Is there a way I can check what wattage rating an unknown resistor is rated for? I mean, I'm guessing just based on size. If I could just see a bunch of resistors and their wattage ratings next to each other and see the sizes of the higher wattage rated resistors, that would pretty much be a dead giveaway to give a ballpark of what kind of wattage can be handled. By a given resistor of a given size. We do want a 5-watt resistor though, that's for sure. Let me check the resistors I bought before. Let me be right back. Okay. So my solder sucker worked. First time ever using it. And works like a boss. That's pretty fun. I didn't think I'd be able to get it down that quick. I thought I would fail and then have to look it up on YouTube to see how to do it properly. I assumed it would be harder to figure out, but it was just super easy. I just instantly got it perfect. Alright, it's a 3-watt resistor, I can pretty much tell. Check this out. So, the question was, we managed to salvage these two resistors, and one was a 5-watt, the white one. You can see it says 5 watts. And what was this? We didn't know. Well, I just found a very similar sized resistor to it right here. And these are three watts. You can see it says it right there. 3 watts, 39k ohms. 3 watts. And they are well, about this size. Very similar. This is closer to the camera, so it seems like it's bigger, but if I put it down next to it, you can see they're pretty much identical size. So it's safe to assume that this is a 3-watt resistor. And yeah, so that was a cool way to identify the sizes, because some actually say it on there, which is quite nice. So that saved us from kind of being lost. So that's another example of it being good to have a horde of circuit boards. A lot of good information can be gleaned. So we were able to identify the wattage that this resistor we salvaged can handle. But we're still kind of in trouble. Because that's not enough watts for our needs. Still comes down to 155. No, it comes down to 4750 plus 460 is the total resistance, which is 5200 ohms. 155 volts, which is going to be what's passing through it, divided by 5210 is 0.0297 amps. 155 times 0.0297 equals 4.6 watts. And this is only rated to 3 watts. It will be fine to have my 5 watt one involved, but my 3 watt one isn't going to cut it because it's 4.6 watts that's going to be passing through it. Now, what I'm thinking of next would be, what if I put two 1000 ohm resistors in parallel? That would give me 500 ohms resistance, because when you use resistors in parallel, it gives you 1/2 the resistance. But by having it in parallel, the electric takes a wider path through 2 different resistors instead of 1, and so that cuts down the total number of watts in half going through each resistor. So if you used 2 3 watt resistors in parallel, that would give you 6 watts of resistance, basically, since only half the wattage will go through each one. So my 4.6 watts would be divided by 2, giving me 2.3 through each one, and they're rated for 3, so they'd be okay. But we would need to have 2 1000 ohm resistors to pull that off. Or we could do 2 460 ohm resistors maybe, which would give us a resistance of 230 ohms. I wonder if that would still work for our stuff. Let's see. 165 times 230 divided by 4750 plus 230. $7.6. Wait. Or we could use 4 of them, 2 in series and 2 in parallel. That would still divide the spread of flow by 2, because it has 2 paths, and then we'd still retain the same resistance if we use 4. I bet you I can get 4 460 ohm resistors. Maybe. Let me show you guys what I did. So, I bought 10 pieces of 5 watt 5.1 k ohm resistors, and it's about $4 for a pack of 10, which comes out to about 36 cents each. If you buy 2 of them, you get a deal on shipping. They cut the shipping down, so 36 cents each. So that's 36 cents per project for the 5k ohm. And then I bought 3 watt 10 piece for 910 ohm value. Now we can put two of these in parallel in order to get 455 ohms of resistance if in parallel. And also when in parallel, you pretty much get 6 watts because you're dividing the total current flowing through when it's resistors in parallel by 2, but you're also cutting the resistance in half when it's in parallel, 2 of them in parallel. So that'd be 910 divided by 2, which is 455 ohms of resistance. So coming over to here, we could do 5.1k ohms. Wait, no. We're not typing it again. Alright, so it's going to be 5.1k ohms. And then this one is 910 ohms. But we do 2 of them, so that will look like this. Alright guys, so the total resistance we wanted for this second resistor in our voltage divider was ideally around 500 ohms, according to our math. In this one we wanted around 5k ohms. 5k ohms plus 500 ohms would give us around 20 to 30 milliamps, depending on voltage highs and lows. And 20 to 30 milliamps times our voltage, which was between 10 to 13, gave us approximately half a watt of power coming off of these lines. And half a watt of power was about double what an Arduino would take, so that's a nice conservative estimate, and we wanted that. So that's a good thing, that good nice amount of power to come off of this thing to feed our circuits. Now, to get 5k ohms, the most popular resistor was, for the price anyways, right here, 5.1k ohms at 5 watts it can handle. 10 pieces for $4, including shipping, and that's even cheaper if you buy more than one quantity of 10 pieces. So buying in bulk helps there. And so that's about 38 cents for this part. And then for these two, we wanted 500 ohms, so I was looking for a 5 watt 500 ohm resistor, but I couldn't find it. I guess I could try it to check, but I couldn't find anything like that. Let's see. Five watt 500 ohm resistor, ceramic. Oof. 44 cents. This other one though that we ended up going with was a lot cheaper. But we needed 2 of them. 910 ohms, 10 pieces, 14 cents, 28 cents. 30 10 cents cheaper. I'm gonna have to go with Dak nabbit. Alright guys, so I just changed my strategy. We're going with the 5 watt 500 ohm 10 pieces for 450, so that's 45 cents each, plus $4 for 10 pieces, about 40 cents each for the 5 watt 5.1 k ohm. So those are our two for our voltage divider. So we've got to update this. Oh my gosh. Let's just undo until it gets right again, how we had it. Thank goodness I set up the Photoshop Unlimited Undos hack. This would be a mess otherwise, try to redraw it all. That was a lot of work. Okay, that's correct now. We're going to go with 500 ohms, and here's 5.1 k ohms. Let's do the math again. Also, we need to put in, this is 500 ohms, and it's 5 watts. And this one is 5.1 k ohms. Okay. We are supplying the Arduino with around half a watt of possible power that can get through this voltage divider, despite only needing 0.225 watts for the Arduino and an unknown wattage to switch on and off. The MOSFET's probably extremely small. It is fine to supply too many watts, just not too few. The extra watts will not actually be used as long as our load does not try to pull that many. The resistors are only rated... no, that part's wrong. The resistors are gigantic and are rated for 5 watts rather than our normal 1/4 watt resistors, because they need to handle the large current running from the 155 volt DC line through the voltage divider This comes out to 5600 or 155 volts divided by 5600 ohms. .28 4.29. $120 divided by 5600. .021. And then 165 divided by 5600 equals 0.029. And then plus 460. Okay. 10.71. 165 times 500 equals divided by 5600 equals 14.73. .43. Yep, perfect.